and today we're going to be talking about finite sums. We're going to be essentially looking at the reverse of finding a derivative. So the basis of this comes from, in the derivative, that was finding the instantaneous rate of change, and that led to which led to the discovery of the slopes of tangent lines and ultimately the derivative. But in addition, to describe how functions change in any given instant, they needed a method to describe how those instantaneous changes could accumulate over an interval to produce the function. So they investigated areas under curves, which led to the second main branch of calculus called the integral. Okay? So we're going to be looking at the first few steps of an integral. So what you see here, the fundamental theorem of calculus, which we will get to in later sections in this chapter, is what brought the differential, which is finding the derivative, and an integral, which is going to be based on area calculus, together. So let's look at this. So let's consider a problem, okay? Okay, so area is a space in here, as you should know. So let's look at this. So consider this problem. A train moves along a track at a steady rate of 75 miles per hour from 7 to 9. What is the total distance traveled by the train? Okay, well, let's look at this. So we got the time is 2 hours. The speed is 75 miles per hour. Okay, and what's the total distance? Well, distance is the rate times time, which is going to be 75 miles per hour times 2 hours, which is 150 miles. And that's what makes this. So if we look at this, we got area is the length times the width, which is going to be the 75. So 0 to 75 and then 7 to 9. 75 times 2. Okay? But what if the velocity varies over a time interval? So imagine the time interval being broken up into many tiny rectangular subintervals, each one so small that the velocity over it would essentially be constant. So imagine you make a lot of itty-bitty little rectangles. So just like this is a rectangle, you're looking down here, and you're making little length times width, length times width, length times width. So just they're itty-bitty, they can go infinite amount of time, okay? So a lot of subintervals. So in one of these subintervals, you're going to have a length times a width, okay? So just as the total area could be found by summing the areas of the rectangular strips, the total distance traveled could be found by summing the small distances traveled over the tiny time intervals. So if we took each area of this, so if I got an area of this little rectangle and that little rectangle and that little rectangle, the sum of these rectangles would have eventually give me the area under this curve. Okay, so let's keep going. All right, so a rectangular approximation. So we're going to be talking about a few of these, and then in another section we're going to be adding 2 additional ones. But this topic is also in BC calculus as well, but this is an introduction to the integral calculus for AB. Okay, so rectangular approximation method. So that's Rram. So pretty much it's the time of the particle, which will be given to you over the number of subintervals. Okay, and what you do, you multiply this by you'll be given one height and evaluate that height and put it into the function that would be given. Okay, this will be the second rectangle height. You'll evaluate that into the function given and then add, same thing. So h is the height of the rectangle. So let's look at the first one, midpoint rectangular approximation method. So the base is determined by the width of the subinterval, and you're going to finding the midpoint of a subinterval to obtain the height of a rectangle. Area is the base times the height. This is the base, that is the height. Okay? Base times height. And then you're adding them all together, just like we were talking about here. You're summing them all together. Summing the areas of the rectangular strips. So that's finding the midpoints. Okay, so this is for this one, you're going to be starting here. You'll start at the furthest to the left endpoint you have, and you go, go, go. You do not include the right endpoint here. Okay, for the right hand endpoint, you do the opposite of the left hand part. It might be easier for you to start at the complete right hand side and then go, go, go. Just do everything except for the left endpoint. Okay, so let's do an example. So a particle starts at x equals 0 and moves along the x-axis with a velocity equal to t squared. Okay, so that's our function that's going to be given. So if you want to, you can put like v, v, v. That might be better for you. There you go, v's. Where is the particle at time equals 3? So that is our time of the particle, which is going to be 3. Approximate the area under the curve using 6 rectangles. So that's your subinterval. So 6 rectangles. Okay, so let's look at this. Let's make 6 rectangles. So we got 1, 2, 3. And it'll go on 0, 2, 3 seconds. So this is 1, 2, 3. So this is going to be my right endpoint here. Okay. And then you're going to want to make some in between, because you need 6 of them. Okay, so you got 1, 2, 3, 4. Oh, I forgot this one. There you go. So you got your 6 subintervals here. So I just traced a line down here, here, and here, and then put lines in between them. So you got 1, 2, 3, 4, 5, 6 rectangles. So let's go ahead and put what those points in. So we got 0 and 1. So this is going to be 0.5 right here. That's going to be 1. That's going to be 1.5. 2, 2.5, and 3. So we're going to be doing the left endpoint, the midpoint, and the right endpoint. So let's go ahead and find the midpoint, and we'll use a different color for that. We will use green. So the midpoint is going to be, the first one's going to be between here and here. So that's going to be 0.25. This is going to be 0.75. This is going to be this is still going to be 6 rectangles. That's going to be 1.25. That's going to be 1.75. This is going to be 2.25. Okay, and this is going to be 2.75. Okay, and if you count the green, you're going to have 1, 2, 3, 4, 5. So you got 1. Oh yeah, 1, 2, 3, 4, 5, 6 rectangles. Okay. So Lram, you're going to start at the furthest left endpoint. Okay. So you're going to be looking at the furthest left endpoint, which is going to be 0. So you got time of particle and time of subintervals. 3, 6 reduces to 1/2. Okay. And now you're going to do, so multiply that by the left endpoint, which is 0. So you do f of 0 plus f of 1, or I'm sorry, f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. 2, 3, 4, 5, 6. So we got 6. We're looking for 6 subintervals. We should only have 6 numbers here. Okay, so this is the numbers of what I used. I'm going to use this one from another segment so you can see better. Okay, so this is the furthest left endpoint. This is where you start. So you got f of 0, f of 0.5, f of 1, f of 1.5, f of 2, f of 2.5. Don't count the right endpoint. Okay, so our function, oh, I should have used v instead of f. V. Why am I using v? Because our function is using v. So now you're going to have 1/2 of 0 squared plus 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared. Okay, where are you getting squared? You're putting in this value in here. So you got 0 squared plus 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared plus 2.5. That's what you get. And your answer is going to be 6.875. Okay, Mram. So that's when we're using the little green numbers here. So you're looking for the midpoint between the rectangles. So you still got 1/2. And now you're going to be doing v of 0.25 plus v of 0.75 plus v of 1.25 plus v of 1.75 plus v of 2.25 plus v of 2.75. Okay. Put it into the equation, t squared, and you get 1/2 0.25 squared plus 0.75 squared plus 1.25 squared plus 1.75 squared plus 2.25 squared plus 2.75 squared. Add them all up, multiply by 1/2, and you get 8.9395. Okay, next one. So this is the right-hand endpoint rectangular approximation. So you start over here at 3. So we're going to be using, you can either start here or you got 0 here and you start at the first purple you see at 0.5. Whatever you want to do. If you want to start the right endpoint so you remember, well, I'll do it that way. So you got f of so all the purple, f of 3, f of 2.5, f of 2, v, sorry, I keep using, there we go, plus a v of 2, plus v of 1.5, plus v of 1, plus v of 0.5. 1, 2, 3, 4, 5, 6. You also get 6 right here too. 1, 2, 3, 4, 5, 6. So same as the others, your function you're using is v of t equals t squared. So you got 1/2 times 3 squared plus 2.5 squared plus 2 squared plus 1.5 squared plus 1 squared plus 0.5 squared, and you get 11.375. So what this tells you, if you're using the left endpoint, it's saying that the area under here is approximately 6.875. Midpoint believes it's 8.9395. Right hand endpoint or right hand rectangular approximation method will give you 11.375. That's trying to get the area under here. Later on, we will use another finite sum that actually will give you the most accurate definition of this. And that sums up rectangular approximation methods.